Good afternoon, everyone. Thank you for being here. I'm Heather Gatney, and I'm the coordinator of the CVFS webinar series. I'm joined here today by Emily Treleaven, Research Assistant Professor at the Survey Research Center at ISR. Emily is going to present on how to link individual, household, and neighborhood level data files. And then after Emily's presentation, we'll show a pre-recorded presentation on linking external data sources to the CVFS. The recording is prepared by Adrienne Epstein. She's a PhD student in epidemiology at the University of California, San Francisco. After that, we'll have time for a Q&A. We ask that you remain muted until then. During the Q&A, you may unmute and ask your question, or you can submit a question at any time today using the chat feature. We'd also like to remind you that this webinar is being recorded. If you have any objections, you may disconnect at this point. A recording of this webinar and the slides will soon be available on the CVFS website. If you missed our first two webinars from September, those are also already available on the website for you to watch. And with that, I will turn the presentation over to Emily.
Great, thank you, Heather. Hi, everyone. I've been working with the Chitwan Valley Family Study since 2017. I primarily use CVFS to study children's health and well-being and how it's shaped by various factors at the household level, like parents' migration and household receipt of remittances, and at the community level, looking at the health service landscape. I've also collaborated on studies that use CVFS data to study migration as an outcome, including work with Adrienne, my co-presenter, on drought and migration. Adrienne is unable to join us live today, so we have a pre-recorded video from her, and then she's also offered to answer follow-up questions via email. I'll first give a refresher on the CVFS sample, how it was selected, and relevant features for understanding the sample and study organization. I'll then quickly overview key CVFS data files, how they're organized, and how they relate to each other. Next, I'll cover how study IDs are structured, how to carry out various types of merges, and specific considerations for different types of merges. Then Adrienne will cover how to merge in external data to CVFS based on GIS or spatial data, and walk through an example of a recent study we did with Nadia Diamond-Smith and Deirdre Gamiri on drought and migration that use CVFS data on migration and non-CVFS data on rainfall. We'll have some time for Q&A. And then I also wanted to know what we're not covering, which is how to carry out merges in various programs like STATA or R. But I did include some resources on merging in STATA, R, and SAS at the end. So we'll start with the sampling frame for CVFS. Looking at the inset map here, the Chitwan district is located in south central Nepal on the border with India. The district includes a large national park along the border with India, and the eastern and western parts of the district are separated by dense forest and Narayangat, which is the urban center. The CVFS study area is in the western part of the district, bounded by the city and forest on the east and rivers on the south and northwest sides. To illustrate the distribution of neighborhoods across the study site while maintaining respondent location confidentiality, this is a map of the study area that shows health facilities rather than enrolled neighborhoods. But our neighborhoods are similarly distributed across the geographic area. On this map, different colored dots represent different types of health facility. First, this map clearly illustrates the natural borders of the CVFS study area, the forest and the national park, the urban center, and then the rivers. The right 1/3 of the study area is more urban. The middle area was rural when the sample was drawn, but has become increasingly peri-urban over the last quarter century. And the left part of or western part of the district remains pretty rural. These are the three strata that were used in the original CVFS sampling frame. When the study was designed in 1995, the geographic area was divided into clusters of 5 to 15 households each to draw the sample. All households in the study area were included in the sampling frame. So essentially, artificial boundaries were drawn around groups of households of that size. The original sample included 121 systematically sampled neighborhoods, 10 neighborhoods that were oversampled to increase representation of specific ethnic groups, and other neighborhoods were added to the sample to reach 5,000 individuals in 171 neighborhoods. In 1997, due to budget constraints, 20 neighborhoods were dropped. So all of these were neighborhoods that were intentionally oversampled in the middle strata that rural, now peri-urban area. And individuals and households in those neighborhoods are no longer followed in the study. So they show up in the 1996 data, but don't appear afterwards. We observe a change in the number of households in sampled neighborhoods over time due to attrition, migration, and growth. So neighborhoods now might be less than 5 households or more than 15. I also wanted to note that over the course of the study, 2 neighborhoods washed away due to flooding. So the households in these neighborhoods moved to nearby areas and are still tracked over time as a part of CVFS. It was thought that these households would return to the geographic area that flooded, but they still haven't. So these 2 neighborhoods show up in the study, even though there are no households that are currently living there. So I've talked about neighborhoods, households, and individuals as part of the CVFS sample. We can think of the sample as a set of all households in the sampled neighborhoods, and the study includes all individuals in those households. So this means that people in the same household are linked, like spouses or parents to children or siblings. 2 other notable features that are important for understanding merges and conceptualizing the data are that CVFS is a panel study. So we have measures over time, meaning that units can be linked from time A to time B, and even to time C and time D. And CVFS follows all individuals regardless of their location. So an individual or household's location is not static over time. To further visualize our data structure, this is a reminder that we have individuals nested within households and households nested within neighborhoods. We also have contextual data that covers the entire study area in Western Chitwan, not just the sampled neighborhoods. And this includes things like services, like schools and health facilities, as well as ecological data. There are a few other important considerations for understanding the CVFS sample and merges. First, the study has very low loss to follow-up. I do want to point out one notable change in 2008, and that was to maintain representativeness of the sample for Western Chitwan Valley at that time. Households who had moved out of the study neighborhoods between 1996 and 2007 were no longer followed beginning in 2008 or later. But everyone who was included in the study in 2008 is still followed today. So how does someone enter the CVFS? One way is by being born into a CVFS household or marriage into a CVFS household, or another means of joining an existing household, like a child who's adopted. When a new household moves into a sampled neighborhood, into that defined geographic area, the household and its members are enrolled in the study. And when 2 or more members from an existing household leave to form their own household, they are split off into a new one. For example, an adult son and his wife might be living with his parents in a CVFS household and then later move into their own house. So they would be considered split off and assigned to a new household within the study. Individuals can leave the sample through death or loss to follow-up. And I want to remind you that since we do follow individuals regardless of their location, we think about this as true loss to follow-up, not just moving out of the study area. So given all of these changes to the panel over time, when you merge individual or household files from 96 to 2008 to 2016, you should never expect a one-to-one merge due to attrition and enrollment. The panel is changing over time. I'll now provide an overview of the different types of data files that comprise CVFS and how they're organized. Generally, data that's collected at different time points has been processed as separate data sets or data files. So if we want to observe a unit over time, we may need to link 2 or more files. We can merge information about the same unit, either individuals, households, neighborhoods, schools, or health facilities, over time. We can also merge information about higher order and lower order units, like matching individuals to households or neighborhoods, and we can merge information about 2 different individuals, like spouses or siblings. This is the study diagram from our study website, which I linked to at the bottom here. This shows all the different types of data files available for analysis through ICPSR, the data repository hosted at U of M. Don't worry about trying to read this, it's just to give you a sense of what's available. These blue files represent public use files, green means restricted use, and orange mean files that are in process or planned for deposit with ICPSR. On this screen, we see various individual files. Individual level data are data sets where the unit of observation is the individual, or each line in the data set is a unique individual. Many of these individual level files are available as either public or restricted use. We can see, for example, that individual interviews were done at 3 time points: 1996, 2008, and 2016. So a user might be interested in linking the data for the same individuals across those 3 time points. I want to point out that we actually have some merged files already available for analysis. For example, a file that merges the 1996 and 2008 individual interviews into a panel. Similarly, we have some files at the household level, and in these, each line in the data set is a unique household. These are data that include measures that apply to all members of a household, like consumption or ownership of durable goods that can be used to measure household wealth. And then we have a number of neighborhood or community or area level files, some of which are already merged for the same area level units over time. All of our area level files are restricted use because they include GIS coordinates. So interested users need to apply for permission to access them through ICPSR. And there are instructions for how to do this on both the CVFS website and the ICPSR website. Like we saw in the study diagram, we have a number of individual level files. The household registry is a household interview, but data are recorded at the individual level. This includes monthly location measures for individuals and monthly level measures of other individual characteristics like school enrollment. Individual interviews are in-depth interviews done for a specific subsample at certain time points. Generally, all people in CVFS households that were ages 15 to 59 and their spouses at the time of interview, broadly excluding children and older adults. The life history calendars or retrospective event history calendars collected at the same time as the individual interviews and include information like work history. We've also done some other topical surveys over the course of the study for specific subpopulations, like child health, measuring health outcomes among all children under age 18. And we'll present on some of these in other webinars this year. Finally, the relationship grid maps how each individual in a household is related to each other. And we'll look at more detail on this in a moment. We have a smaller number of household level files. And as I noted, these include information on household land use, durable goods, and remittances. And then we have study, neighborhood, and contextual data. The neighborhood history calendars map a wide range of neighborhood services and groups, and these are based on the study definition of a neighborhood, that geographically defined area. So these are specific to CVFS neighborhoods. Then we have other contextual files that cover all of Western Chitwan, not just CVFS neighborhoods. For example, we have data on the annual characteristics of the universe of schools and health facilities in the area, and then additional data on biodiversity and community land use. So now that we have a brief overview of the types of data sets at different levels, we'll move on to talking about merging. The key for understanding how to merge observations, especially across levels, is understanding how IDs are structured within the CVFS. The structure of IDs has changed over time, so I'll first review the prior structure that was used from 1996 to 2007, and the current structure, which has been used from 2008 onwards, and how to convert in between the 2 types of IDs. There are 3 types of IDs in the CVFS: the neighborhood, household, and individual. Neighborhood is a 3-digit ID assigned sequentially from 1 to 171 for each neighborhood that was in the original 1996 sample. At that time, each household in each neighborhood was assigned a 2-digit ID, and each individual in each household was also assigned a 2-digit ID. So to identify unique households in the study, we have 5-digit IDs that combine the 3 digits of neighborhood and the 2 digits of the household appended. And individuals were uniquely identified by combining the 5-digit household ID with the 2-digit individual ID. For example, person 2 in household 5 in neighborhood 21 would have the ID 021 for the neighborhood, 05 for the house, and 02 for the individual. Starting in 2008, CVFS moved to a 9-digit ID format by adding a leading 0 to the household ID and a leading 0 to the 2-digit individual ID. So now each of the 3 components is 3 digits, creating a 9-digit individual ID and a 6-digit household ID. So using our previous example of person 2 in household 5 from neighborhood 21, that person's ID would now be 021, 005, 002. To convert from the 7 to the 9-digit ID, we add a leading 0 to the household, and then we add a leading 0 to the 2-digit member ID. I've mentioned accessing CVFS data files through ICPSR and that there are both public and restricted use files. There are some specific considerations for each depending on which kind of file you're working with. Public use files are immediately available for analysis, and restricted use files require the user to apply for access and go through an approval process with ICPSR. Our public use files that were released on ICPSR prior to 2016 use consistent IDs, meaning that the same individual or household will have the same unique ID across all of these files. Public use files released on ICPSR in 2016 and later have scrambled IDs, meaning that the same individual will have different IDs across each of these files, so they cannot be merged or matched across files. Only restricted use files include area level or GIS information to protect respondent confidentiality. Restricted use files use consistent IDs regardless of the release date, so the same individual or household will have the same unique ID across all restricted use files. And again, for the public use files, I want to reiterate that the IDs depend on the year that the data was deposited with ICPSR, not on the year that the data was collected. So turning to merging, we'll first talk about merging data about an individual to other data about that same individual in a different data set. This is called a one-to-one merge because we're merging a single observation in one data set to a single observation in another data set. In CVFS, individual IDs are called the respondent ID or RESP ID as the variable name. Remember that the RESP ID was 7 digits until 2007 and then 9 digits from 2008 onwards. Some data files include both the old respondent ID that's 7 digits, called RESP ID _old, and the newer 9-digit ID called RESP ID for the same individual. Older files may use the 7-digit ID, but call it RESP ID, so the user needs to be careful in checking the number of digits prior to merging. To merge to another individual in the household or data set, you would need to have a variable for each individual that contains the unique respondent ID for the other individual you want to merge them to. So for example, let's say I wanted to merge information about spouses together. I would need to have a variable in my data file that contains the ID or RESP ID for each individual observation spouse. And generally IDs for other observations, other relatives or people living in the same household will come from the CVFS relationship grid. The CVFS relationship grid provides individual IDs by relationship type to every other individual in a household. And I want to note that an individual did not have to be physically present in a household at the time of the relationship grid to be included as a household member. So for example, a migrant working in Qatar appears in the relationship grid with his current household, even if he's in Qatar and his other family members are all in Chitwan. We've created relationship grids at 4 time points: 1996, 2001, 2008, and 2016. Currently, the time 1 relationship grid is available through ICPSR, and we're working on making restricted use versions of later time points available soon. This is a snapshot of the relationship grid where the IDs are scrambled to protect respondents. So here we see that we're using the current 9-digit ID format, starting with the 6-digit household ID. So this would be neighborhood 212, household 7. For this first observation, we see the respondent's ID, as well as the ID for his or her spouse and their 3 children. The spouse is on line 2, so we see this is the same ID here and here with their spouse, the same person from line 1, and then the same 3 children. Then we have observations for each of the children, and we can see their parent IDs because they are the children of the parents in this household. So each individual in a CVFS household appears as a unique observation in this data set in the relationship grid, with the IDs of all of their other household members listed by relationship type to that person. Turning to households, similarly, we can do a one-to-one merge of households across files since they're the same unit of observation. The household ID variable is called HHID in CVFS data files. And again, users will need to be careful about using 5 versus 6-digit IDs since they will not merge to each other. You'll need to convert to make sure they're consistent across the files that you're merging. Finally, we can do a one-to-one merge at the neighborhood or service level, meaning neighborhood to neighborhood or school to school, for example. Neighborhoods are called either NAID or NBHID in CVFS data files, and health facilities and schools tracked in the health facility calendars and school history calendars also each have unique identifiers. These area level files also include GIS coordinates. In CVFS, we use UTM XY coordinates, which Adrian will go into more detail on. And while neighborhoods can easily be matched to households and individuals, all of the other contextual data, the services and ecological data, have to be merged to neighborhoods using GIS coordinates. We can also merge across different units. This is called a many-to-one merge, where we merge multiple or many observations at the lower level to a single unit at the higher level. For example, to give a non-CVFS example, merging all students in a classroom to their teacher or to their school, or in a CVFS example, merging all individuals in a household to a specific household ID. And there's some specific considerations for this type of merge in CVFS. First, the household component of an individual ID is derived from the household where that individual was first enrolled. So this household component of the ID may not match that individual's current household because individual IDs are not reassigned over time. So the user should check the household registry for the current household ID of a given individual in a given month. This can be done in the registry using the variable HHID month. For example, at month 180, a user could look at the variable HHID 180 to find the household ID for a specific individual in month 180. For example, we could think about a woman who was born into a CVFS household and assigned a respondent ID at birth. She later marries a person in another CVFS household and moves to that household upon marriage. Her household ID will change in the registry on the month that she moves into her marital home, but she will retain the same respondent ID over time. So once she's moved into her marital home, if you abstracted out the middle 3 digits of her ID, they would not match the 3 digits of the household ID in the household registry for her observation. To merge individuals to neighborhoods, we can again do a many-to-one merge. And similar to households, the neighborhood component of an individual's ID may not match their current location because they are also not reassigned after a person moves. So again, the user should check the household registry for the location of a specific individual in a given month. This can be done using the location variable, for example, loc 180, to find the exact location of an individual in month 180. We can also merge households to neighborhoods, which again would be a many-to-one merge. And again, the registry can be used to find the neighborhood location in a given month. But remember that that registry is at the individual level, so it provides household members' location in a given month. And different members of the household may have different locations at a particular time. Finally, as I've mentioned, we can merge our CVFS area level data to non-CVFS data that includes GIS measures, which Adrian will now discuss. So Heather, I will turn it over to you to show Adrian's pre-recorded video.
Hi, I'm Adrian Epstein. I'm a PhD student at UC San Francisco in epidemiology. And I've been working with CVFS data for the past couple of years. And I'm going to talk a little bit about using spatial data in the context of CVFS. So first, I'm just going to give a very broad overview on spatial data in general and different types of spatial data, just to get everyone up to speed. So one type of spatial data is raster data. Raster data is basically gridded pixel data. Each data point is stored as a pixel, for example, as pictured on the right. Each pixel has one unit of information, and this is often how satellite or photographic image is stored. So examples of raster files include elevation is usually stored as a raster, precipitation, land use types, population estimates are usually stored as a raster where it's a continuous surface and every pixel has one value. So the resolution is really important when working with raster data. So the resolution is essentially the pixel size. So one example could be if you have 5 kilometer by 5 kilometer pixels, and the higher the resolution, the more clear the image is basically, and then more number of pixels you have. So for example, on the right here, you have 1 meter resolution. That's really high resolution. You can see the picture is very clear. Whereas on the left, you have 8 meter resolution, which is much more pixelated. In addition to raster data, there is also vector data. So vector data are scalable data that are geometrically representing points, lines, or polygons. And what you use vector data for is to represent boundaries, roads, regional areas, etc. So if you have a map, typically what you're looking at is vector data. So like I said, there's 3 types of vector data. One type is points, for example, here showing health facilities in Namibia, lines, for example, this network of roads, and polygons such as these districts in Uganda. And most maps tend to overlay points, lines, and polygons. You can combine them to have a map with like, of the US states and the road network over them. So how are vector data stored? They're stored in what are called shapefiles. And shapefiles are comprised of the following 4 files. They each have these different extensions, .shp, .dbf, .prj, and .shx. It's not super important what each of these files does, but what is really important is to know that you need to keep all these files together in the same folder. So if you're sending shapefiles, you should probably just zip them into one folder, or if you're storing them on your computer, make sure to keep them all together in one folder. Coordinate reference systems, I'm not going to talk too much about them today, but they're very important, and it's really good to know what CRS or coordinate reference system your shapefile is in. So what is a CRS? Well, of course, to make a map, you have to convert a sphere or a 3D object into a 2-dimensional map. And when you do that, you're going to create some form of distortion no matter what. So picking a CRS is important, but even more important is just to make sure that everything that you're working with, if you're working with multiple shapefiles or if you're working with a raster data and a shapefile, you need to make sure that all of your data are in the same projection. So a really common projection is WGS84. I will talk about it a little bit in a bit when I show you some code. But like I said, just make sure all the layers in your map are using the same projection. And I have here a very good resource of reading more about CRSs if you're interested. So now jumping into spatial data in CVFS. So how are spatial data represented in CVS? Well, neighborhoods are stored as points, and these points represent the centroids or the center of each neighborhood. So if you, for example, you have access to the restricted data set in CVFS, you can load in this data file, which just has NX, NY, and the neighborhood ID. So this is not yet a shape file, it's just a flat file with latitude and longitude. And I should note that we're not actually going to show the latitude and longitude to protect privacy and confidentiality. But if for some reason or someday you get access to the restricted data set, this is what the data will look like. So you might have seen in the slide before when I wrote latitude and longitude, I put UTM in parentheses. That's because latitude and longitude here are represented in universal transverse Mercator projection. This is actually not a very common projection to use unless you're working in a very small area, which I suppose CVFS is. What UTM is each, it's basically each of these squares or rectangles across the globe has its own mini projection. So in Chitwan is actually located in zone 45 over here. And you need to know what zone you're in if you want to convert UTM into another projection, which I'm going to show you as we do in the code. So I had to look up which zone Chitwan was in order to convert neighborhood coordinates into a different projection. So I'm just going to give an example of working with CVFS data. So say now I have these point locations of where the neighborhoods are, and say I have a raster data set and I want to see what the value is of that raster data set in each neighborhood. So just as a very toy example, I took a raster data set from the demographic and health surveys. DHS models raster surfaces for a bunch of their key variables. And so I took one which was the prevalence of houses with access to improved water. So I'm just going to show you some sample R code. I'm not going to talk too much about each step, but at the end of this presentation, I've given you my email address. So I'm happy to send you the code or send you these slides if you would like to look more closely at the code. But basically, what this code is doing is first I'm reading in the neighborhood coordinates, that file that I showed you before where you just have latitude, longitude, neighborhood ID. And then here I'm actually turning those coordinates into a shapefile. So this first step, this spatial points data frame step is actually saying, okay, I want to convert these just raw numbers and make them into a shapefile that can be plotted on a map. And here I'm telling R that the latitude and longitude is currently in UTM and it's in zone 45. But the raster data set that I'm working with is not in UTM. It's in another projection, the one that I mentioned before that's used very often. So here I'm converting it into standard longitude and latitude that's typically used in data sets. So this is transforming the shapefile into a new projection. Then here I'm loading in that raster data set that I told you about. So this is where it's located on my local machine. And I just downloaded this raster data set from the DHS. I provided the link in the previous slide. And then I wanted to plot and see what that raster looked like. So here it is. This is all of Nepal, and each pixel represents the prevalence of access to improved water in that pixel. And so now what I want to say is at each point in each neighborhood, what is the value of the raster at that point? So first, I was just making sure that the raster is the same coordinate reference system as what I converted the neighborhoods to, and it was. And then here, this line of code, raster extract, and then you put in the raster data set and then the shapefile, that's actually extracting the raster value at each point. And then I decided to look at what that data looked like. And you can see here, I again have my latitude and my longitude, they're still stored, and then the neighborhood ID. And then here's that new variable I created, which is telling me the prevalence of access to improved water in that neighborhood. So very high across the board, 99, 98%, which is not surprising. So I'm just going to walk you through one more example of how we used spatial data in CVFS. This is work I've done over the past few years with Emily, who is giving this presentation, and our collaborator, Nadia Diamond-Smith at UCSF. And we wanted to look at drought and migration in Chitwan. We've provided here the title of the presentation we gave at PAA this past year, if you want to look up the abstract. But the aim of this little bit that I'm going to describe was to evaluate the association between drought at the neighborhood level and outmigration. So the steps that I'm going to very quickly walk you through was first downloading precipitation data from CHIRPS, which is a publicly available data set with high resolution data set of rainfall, and you can get it daily, 5-day, or monthly. Then I'm going to show you how I generate this drought variable. And the way that drought is defined is how much did rain in the year prior to the survey deviate from the prior 29 years. And then extract the drought status at each neighborhood for each month of observation. And then finally merging monthly drought and neighborhood information with household registry data. So I'm going to walk you through these steps and show you some code with how we did that. So first, downloading the precipitation data from CHIRPS. I'm just showing code here of how you can do that in R, so you don't even have to go to the CHIRPS website. You can download from FTP. I'm not going to walk through this code, but again, if you would like this code, it's really handy if you want monthly or even 5-day or 1-day rainfall. You can use this code to download it. And then I generated a monthly drought variable. This was defined as a rainfall percentile deviation in the past year relative to the last 29 years. So basically what you end up getting is the value represents the percentile of rain in the relative to the past 30 years, basically. So if you have a value of 0.5, that means in the past year you experienced the median level of rainfall that you have also experienced over the past 30 years. And we define drought as below 0.3, below the 30th percentile. So basically what I ended up doing was converting the CHIRPS data set into, now I created rasters for every month of what the percentile rainfall was for that month. And then finally, I extracted the drought status at each neighborhood for each month of observation. So for every neighborhood month combination, extracting what the rainfall percentile was in that month. And that's what this one line of code here is doing. Again, using that raster extract command that I mentioned earlier. And here I'm just showing what the data ended up looking like. So you can see that there are, this is just for one neighborhood. So I'm not showing the neighborhood ID, but it's only one neighborhood. So now for every month, I have what the rainfall percentile was in that month. And you can see that a number of the months in this neighborhood were actually defined as drought, which was below 0.3. And then finally, so now I have monthly drought neighborhood information, and I merge that in with the household registry. So now we know what the drought status was for each individual in each month. And we were able to ask the question, were people more likely to migrate when their neighborhood experienced drought? And we found that yes, they were. So the adjusted odds ratio for internal drought outmigration association was 1.24, meaning experiencing drought in the past year was associated with a 24% increase in the odds of outmigration, and pretty similar for international outmigration with an odds ratio of 1.16. So that's all I have for this brief presentation today. I hope it was somewhat useful. I'm sorry it was a little quick, but again, feel free to reach out to me if you do end up wanting to use spatial data with CVFS, and I'm happy to send sample code or provide some tips on how to move forward. So thank you.
Thanks, Heather. So I think we can go to Q&A now.
Emily, whenever I'm giving a talk, my role is to stay quiet during Q&A, but since you're giving the talk, I can't help myself. How much variation neighborhood to neighborhood in drought can there be? Like, it seems like a really small place to me. Like, I don't get it.
That's a good question. I had the same concern, and I was actually surprised by how much variation we did see. I'm going to see if I can actually pull up.
It didn't have to be a database.
Adrian put together a nice graph of in addition to the spatial variation, though, we had a lot of temporal variation. So we were looking at month-to-month variation over a 9-year period. And so, you know, neighborhood to neighborhood, it didn't change as much as it did from month A to month B.
Yeah, and as you know, I'm not a migration person either, but I sort of started wondering, oh, how much drought do you have to have before you move? That's interesting.
Yeah, I had the same question. I mean, maybe, well, it's just us, so I think it's appropriate to ask for everyone. But what did you look at other environmental variables? Are there other things that, I mean, I've been really dismissive when people ask me like, well, can I put in my this kind of rainfall data? I'm like, no, it's a small neighborhood. You can't put in rainfall data. And now you just told me I can put in rainfall data. So yeah, I'm wondering about, is there a lot of variation that we've been missing that these, our recent Nobel laureates would want us to be using to identify causal relationships?
I'm sure David would be, by the way, for whatever that's worth.
Yeah.
I would say it depends on how long of a temporal period you're looking at, and you would need a sufficient temporal period to get, in my mind, that's the more important source of variation. We plan to look at heat and flooding, or I guess it's not, we don't technically have flooding measures. It would, I guess that's what you would call excessive rainfall. We're going to look at those because we're also working on a project looking at low birth weight. Nadia and Adrian received from funding from UCSF to look specifically at climate and obstetric outcomes. So we're going to take a look at that, but we'll add in some additional climate variables into that next analysis.
I am totally going to be quiet so that the rest of our guests have a chance to ask questions too. But before I am, there is interesting topographical variance within Chitwan and how dry the land is already. There is wet land and dry land within Chitwan. And I would think, particularly if it's sort of lack of agricultural productivity driving people to consider moving for jobs, that the interaction between the rainfall data and where that land lays would be quite interesting to investigate.
Yeah, and we've also looked at their livelihood source. So considering that, was it someone that was in farming, and how does that relate to their risk of migration?
I have
Coulter, yeah.
Yeah, I have a quick question. Although I'm also tempted to go down the line of all these substantive and methodological questions about error to variance ratios and things like that. Let me go back to merging. I ask a quick question about merging, which is, so you did a really nice job describing it, and it'll be helpful for people who watch this later on. But, there was a point when you said, we're merging many to one, right? And by the way, that's different from the one to many, which, it's very tricky and you can get very confused very quickly. So when you start doing merges like that, it can, a lot of things can go wrong really quickly. Could you just talk, even just some tips about things that you do to make sure that you haven't messed this whole thing up when you merged many to one or one to many?
That is a great question, Coulter. So I want to, let me screen share again, because there's a specific resource I want to highlight in my list. Let's see here. Okay, so hopefully you see a slide now that says Q&A or resources. Yeah. Okay, great. So this this resource from Wisconsin, I think, does a really nice job conceptualizing differences between merging and appending. I didn't even go into appending because it's not typically something we need to do with CVFS. But differences between merging and appending, and then one to one, one to many, many to one, and many to many, which just blows my mind. And hopefully we don't ever have to talk about that in CVFS. So I think that's a resource I would like, even if you're not a STATA user. I think the conceptual way that they frame it is really helpful. So I would encourage people to take a look at that. So for many to one, I often do work where I'm trying to merge children and parents. So that's a little bit easier because a child can have one mother and one father, at least in the CVFS context. And so usually it's easy to see. I can, if I want to check that I'm correctly merging to fathers, I can check the reported gender and reported age of the people that I'm merging to. So if I merge to someone I think is a father, but then it turns out that's a 5-year-old girl, that's a flag. That is probably not actually that person's father. So I can do that sort of check to check the characteristics of the person that I'm merging to. How close do they match what I would expect? We also know that the TFR, the total fertility rate in CVFS right now is around 2. Many families have 2 children. It was, Sarah, correct me if I'm wrong, I want to say like around 5 in 1996. Sarah put together a nice graph looking at changes in the TFR over time and by cohort. So if I'm merging children to parents, I have a sense of about how many I would expect. Like a family with 13 kids, I don't think there are any of those in the CVFS sample. So if all of a sudden I'm merging, you know, a mother to 13 children, that's also a flag for me. So thinking about what, you know, knowing a little bit of basic information about the context can help identify errors in that sort of merge. Every child needs to have a parent, so it's also a flag when I can't find a parent for a child. That is, you know, a very specific type of example. I'm struggling a little bit to think about a household example, but if there's a particular example you can think of, I can, I'm happy to try and talk through it.
No, I mean, it's been a while since I've merged them from this. Like, I know we talked about this in the past where I seem to know the old data rather than the more recent data. So I have these like, oh, I've definitely merged kids to parents and, you know, and then you have households within neighborhoods and even creating like aggregate measures of neighborhoods from all of the individuals and then merging that on. But some of these things are far more complicated, you know, when you have like these external data sets that you're trying to merge into. And I can, anyway, that's I don't have any specific example.
Yeah, once we start getting to the external data sets, I will happily defer to Adrienne on that because she handled all of that for the project I did with her.
I have a question, but Winnie is my student, so it might be I might be asking the question that Winnie was going to ask. So I'm going to turn it over to my amazing graduate student, Winnie Yang. Most of these people on this call are very old, wonderful collaborators of mine that you will meet in person someday.
Thank you, Professor. No, I just have a quick question about the relationship group that you showed us. So I'm wondering if the child ID from 1 to 13 that you showed us, like, does that follow the birth order or does it not?
Oh, that is a great question. I think in theory often, but it's not a rule, which is a very unsatisfying answer. So the way that I have checked that myself is just checking the age of the individual children.
Yeah, I was going to ask Deirdre what it was supposed to be, but Winnie, I would say never count on it being birth order. I wouldn't trust birth order unless I did what Emily did and actually had it by birthday. But Deirdre, what was it supposed to? Was the ID supposed to be birth order?
No. I mean, it was not rule, but in common, people, tend to answer the questions in order. But it is not real.
Depends on how they
rule.
Yeah.
The
respondent could have replied to the interviewer in some order.
I mean,
so some kind of idiosyncratic where there's, mainly people go in one order, but some people go in the other order, and then occasionally people forget entirely. Oh, right, there's that one kid I forgot entirely, and that could happen.
So this leads to my question though, which is, in the relationship grid, is that like child 1, 2, 3, all the way up to 13, the same numbers as the child lines in the life history calendar, like child 1 school, child 2 school?
No,
it's their IDs.
Yeah. We didn't. We did not make that.
So you have to.
No.
So we have their individual IDs, the kids' IDs on the parents' life history calendar lines. So I mean, you see what I want to do. I want to take these kids.
I
and
see what you want to do. I do.
Yeah.
You got to
No,
start
no.
with these were two completely different field operations.
Right.
The relationship grid data was gathered during the census. So the census was gathered before we even chose who was eligible for individual interview. And then it's during that census that they then do the relationship grid, and it could be separated by months until they go back to a particular household and say, well, everybody 15 to 59 is eligible. Turns out this 35-year-old person had 4 kids, and here's their ages now. Like, I wouldn't even count on those ages matching because a 6-month difference and then any kind of reporting rounding error on both of them, and you could get 1-year age mismatches. So yeah, actually,
Yeah.
that's pretty
Yeah,
complicated.
just to add to complication, like, the relationship grid is a household level data collection. So there could be more than one mother in that household. So it is almost impossible to have that.
In fact, at least 10% of the households that happens.
Yeah.
So
Yeah.
Okay.
Yeah.
So really, we need to just like sort on sex and age and match that way.
we're doing a lot of so we right now have a project linking parents' mental health to their kids' family formation. And it has been a beastly tour for me of all the complications we've created across the past 25 years. And it does require, you have to decide what you have first, and then what second, and then what third. And so this order in which you search to match starts to define you're defining the universe you're matching one way or another. And in that case, it's sort of, you have to have had a mental health interview to be an eligible parent for this analysis. And then you have to have a kid as identified in any one of the 4 household relationship grids. And then we got to go find that kid. And we discovered errors in the data, which have now been, we had to go back to the original handwritten stuff to correct these. But, we found some of these, kids who are 20 years older than their moms kind of stuff. And so Emily's point of like sort of checking it that way makes a ton of sense to me, particularly if you're going through one of these complicated within family link things.
Right. And I hadn't thought about that you could have kids that are listed in like the time 4 household grid, but then there could be different kids that were listed in the time 3 household grid.
And Sarah, I'm glad you introduced Winnie as one of your students. Sarah, my favorite tool that I have relearned to use is the Lexis diagram. Lexis diagram is so important for these data because they're broad age range data and then panel data. And so when you say something like a household relationship grid, yeah, what year it was taken from turns out to be totally germane to who's even possible to be a kid of whom. Yeah, absolutely. I wind up putting each relationship grid into the Lexis diagram to try and figure out, okay, what are the ranges of eligibility and who would even be in CVFS? Through this process, Jürgen, I discovered what a bummer that we capped mental health measurement at age 59, because of course there were a bunch of parents who are older than 59 now.
Absolutely, yes.
And so we don't have one file that is like a household universe grid where it would just link anybody who is ever there. It's always specific to that time.
To a time. It's always specific.
Yeah,
to a
it's
time.
dynamic. You keep adding people, so yeah.
Well, it's worse than that, Durga, because you add people in a systematic way in the registry, but then we've identified these specific years, 2008 and 2016, where I am going to, in air quotes, we refresh the sample. Now, we do that for a very important reason, just like the PSID adding a new immigrant cohort, because you're no longer representative of Western Chitwan, Nepal if you don't refresh the sample with people who've moved in. But when you do that, of course, you're adding a bunch of people for whom you don't have history.
Yeah.
So those complications are not, I mean, the ability of the data set to do cool things is very high, but those complications are also high.
So in theory, someone could take the household registry and create dynamic relationship grids on a monthly basis. I think, Durga, you said starting in 2011 and onwards, that would be possible. But it's not something that's been done.
And I think in December, we were hoping to have a little bit of brainstorming about new project ideas. I mean, one other comment I'll make, Sarah, and this could be relevant to a dissertation project as well, but for a funded research project, if I had a 5-year R01, I would count on the first year being a bunch of this linking work to get everything in order to actually do what you said you were going to do.
Okay.
Just to put it in some kind of order of magnitude.
2 minutes left. So one more quick question.
Winnie, do we have any other questions?
No, thank you.
A meeting this morning about how to merge kids.
Well, I'd love to have you guys visit
follow-up.
here. I also think sometime it'd be nice to visit there, presumably not January or February, but something.
Sorry, can you guys hear me? Okay, great. Can I ask a quick follow-up? Just to clarify, so you were saying the birth orders are not potential, they're potentially out of order in the relationship grid, but in the LHC, like the child C1L, C2L, that is also potentially out of order.
Yes.
Yeah, I mean, I'll give Durga a moment to think about it, but the interaction between the interviewer and the respondent is asking the mother or father to report all of the live birth children she or he has ever had. And they report them in an order sometimes, but it would be totally feasible that they might skip over one and return to them in another line. Is that not correct, Durga?
I think if you want to work on the parity or the birth order, I would more rely on the life history calendar because of the thought process. Like we ask the marriage first and then the children. So that gives you more, precise measures than the household registry. There is a little bit complication if, for women calendar, that's fine. For men calendar, which we collect children information. I think so. The mother calendar should be more accurate in terms of birth order than anything else we have. And from there, using both the birth year and gender, you may, accurately create the birth order.
Okay, great. Now I'm just doing parity progression for my master's, and I was like, just working under the premise that they were in the right order. So I will double check, but thank you.
Yeah, you can do it, but be careful.
Yeah, and I would definitely check some with the actual birth dates if you have them. That's the best way to check if the order's right.
I mean, in the earlier period, because there are a lot of child death, child mortality, and some of the child might skip. So in the life history calendar row, you see there is a blank row because that child was died, so you cannot get at the end. So that was not listed. So yeah, keep those kind of issues in mind when you are looking at life history calendar.
Okay, it's 3 o'clock. If anybody has any additional questions, you can submit them through our website. You can go to the webinar feedback page, and at the bottom, there's a place where you could enter your email and your question.
Okay.
Thanks, Emily, and thank you everyone for joining us today. Appreciate it very much.
Thanks, everyone. Thanks, Sarah.
Yep.
Bye. Bye.
Thanks.